All right. Hey, everyone. How's it going? Okay. Yeah, that's about where I am. And Nick, I know I owe you an answer. Uh, yeah, end of the semester slump. Yeah. Um, for this class, what I want to say is I'm trying to give you assignments where like you don't have to be perfect on them. Yeah. You don't have to be perfect. Do what you can, and that can still earn you an A. In general, uh, yeah. Wait, what was the? I missed whatever that was. In general, just do something, and you'll do okay. Uh, Currently on the moon. Wait, what? How are you on the moon? I don't even understand that. The sound of doing okay. Yeah. Um, oh, all right. There you go. Good physics there. Um, so yeah, we've got to start on the homework. You don't have to be perfect on it, but there's stuff to do there. Um, I thought that's what they've been saying forever. They're always saying that. Yeah, come to the physics tea if you want to see people. Um, Gosh, you folks. Um, so what I'd like to do today is wrap up with some of the ideas here. We had introduced. Yeah, I know it's important stuff. Let's talk about though light and waves and stuff like that. I wanted to give you all a sense of Brewster's angles and some of the physics and stuff that was going on here. Yeah, we ran out of time last time, so we'd gotten set up with Fresnel's equations, right? And this was for light that's polarized in the plane of incidence, parallel to the plane of incidence. So these were the two equations we have. You can plot them as a function of the angle of incidence for a particular pair of index of refraction. Um, and that's part of your homework actually, is to go ahead and make a plot for air to diamond interface, for example. So the plot looks something like this. You can see that when alpha is small, that's for relatively small angles of incidence, then you get for the right index of refraction combination, you'll get a minus sign in the equation for reflected amplitude. And so that means you get a phase flip upon reflection. And then as alpha gets bigger, beta is just a function of the material, so that doesn't change. But as alpha changes with the angles, then right as the angle changes, alpha gets bigger and bigger until finally this numerator becomes positive. And so in order to go from negative to positive, though, that means that you go through a point where there's zero reflected amplitude, right? And we called that Brewster's angle. And turns out that this is actually only true for, again, for this p polarization right here. So here, give me 1 second. I'm going to put p polarization, right? Polarization right there. If we were to do the exact same thing, but for S polarization, polarization that's sticking up out of the plane of incidence, part of your homework, right? So I'm going to draw that same graph looks like over here. Again, we're plotting the reflected amplitude as a function of the angle of incidence. And let me see something. Yeah, so we get something kind of similar for our transmission, where the transmitted amplitude goes down to 0. Right? At grazing incidence, everything gets reflected. So this was going to be my transmitted amplitude normalized by the incident amplitude. One thing that's different, though, is we're always going to have a positive reflected amplitude that'll go up to 100%, like that. Right? This is my reflected amplitude. So, right, this is what you should be seeing eventually at the end of that homework problem. Something kind of like this. But notice something right here. All right, so I'm just going to quickly label this. This is for S polarization. Perpendicular. Yeah, can the reflected amplitude ever be zero on this one? And that's exactly what I was trying to get at for this one right here, is that, right, there's no Brewster's angle for this S polarization, right? There's always going to be a little bit of reflection. Always some reflected amplitude. We never have that zero crossing. When we met, let's take a second actually before we start playing around with polarizers, if we have them, and looking at what this means. Let's take a look at what we actually observe. And so, as I mentioned before, typically we don't actually observe the field intensity. I'm going to do this kind of off in the middle over here. Right here, this is just an aside. Whoops. Usually what we're measuring is the intensity I. And so we wrote down the intensity before for light in a plane wave, but that was so long as the light was going perpendicular to our surface. If we have the light coming out at different angles, right, the light, it will spread across the surface differently. So really what we're interested in, our intensity, let's write it out this way: how much of the pointing vector goes through the surface. So we can make a surface that's parallel to our interface and say how much intensity is going through that. So let me take and write out symbolically what I mean by that. So the intensity of the incident wave right here is going to be its pointing vector dotted with the component that sticks out normal to the plane of the interface, right? So basically, this is saying how much goes through the interface, and then we're going to take the the time average of that is the one other thing we want to include in there. So we get the 1/2 epsilon 1 v1 amplitude squared part that we had before, but we also got to see how much is actually going through the surface, basically how much is striking the interface. And so we get the cosine term from the dot product. So we can do the same thing for the reflected and transmitted amplitudes. And what we're going to come up with is reflection coefficients and transmission coefficients as a function of angle, though. So same thing. So reflected, so E1, V1, E naught, the reflected amplitude, and then we have a cosine of the reflected angle, which is the same as the angle of incidence too. And then we're going to do the same thing over here. Whoops, that's not what I wanted. Whoa, that's not what I wanted either. Here. The transmitted intensity. So we get a 1/2. Now we're in the second material. Okay, so that's fine. So what's more important to us is to say, well, how much gets reflected? And so that's what, right, our reflection coefficient. How much gets reflected as a function of the incoming intensity? There we go. So to do that, right, our reflection coefficient, we defined this way before. It's the reflected intensity measured in units of incident intensity. So reflected intensity divided by incident intensity. So, I mean, I could write all this out and we get 1/2 E1 V1 R, and over here, I'm doing it small because it's going to, most of this is going to cancel out. E1 V1 E naught reflected over cosine, incident. This was reflected up here. Cosine theta incident. And so everything here is going to cancel except for the amplitudes, right? I can go through here and say, okay, well, my 1/2s cancel, my epsilon 1s cancel, my V1s cancel. The angle of incidence is equal to the angle of reflection, so the cosines cancel. And all I'm left with is E naught R over E naught incident, whole thing squared. They were both squared. Give me 1 second. I want to give myself slightly more room here. Uh-oh. I did some weird things here. All right.
Wait, if they're both squared, then wouldn't the square go away on the right-hand side?
No, so it's E naught R squared over E naught, I squared. And so I could write this as E naught R squared over E naught I squared, or I could write it E naught R over E naught I whole quantity squared. That's what I tried to do right there, right? And so we do all that, and we just have the expression for this right up above. This is going to be alpha minus beta over alpha plus beta, whole thing squared, right? Just from Fresnel's equations up above. And we can do the same thing for transmission, and for that it's going to get a little bit weirder, right? Our transmission coefficient. Transmission coefficient here. So same thing, it's our transmitted intensity over our incident intensity, and we've got 1/2. Now it's epsilon 2 V2 transmitted amplitude squared times cosine of the transmission amplitude. All that over, I'm going to run out of space, 1/2 epsilon 1 V1 E naught incident squared cosine theta incident. And so the 1/2s cancel, and then we can do some other simplifications. So the 1/2s cancel, but nothing else directly cancels. So what we're left with, well, I'm going to run out of space. Right, we've got okay, so we can regroup these things. Everyone's got an epsilon 1, epsilon 2. We can rewrite that actually in terms of epsilon 2 V2, epsilon 1 V1. We can rewrite that in terms of mu's and v's, and then that becomes, and that's our beta, and then our cosine of our angles right here, that's our alpha right there. So all together we do a bunch of math on this, and I don't know, not a whole lot to see. We get alpha beta times 2 over alpha plus beta. Right. Basically, this looks a lot like the second one of our Fresnel equations squared, but we've got this extra product of alpha beta out front because of the extra cosines and E2 epsilon 2 V2 over epsilon 1 V1. So it's, again, it looks the part in the parentheses is coming from the ratio of the amplitude squared, but this part right here is extra because of the extra terms in there. So we can make a plot of these things, and the reason why I was doing all this in this messy way, I wanted to keep up the plots of the amplitude along with this. So this is all an aside. And so over here for our p polarization, I can make a plot of our reflection and transmission coefficients as a function of theta incident. Right, and go up to 90 degrees, and here's 0. And so our reflection coefficient here, right, is just going to be proportional to the square of that reflected amplitude. So it starts out, when we square it, becomes positive. We have where you have that 0 crossing, this goes to 0, and then it rises up to hit 1. So this is my reflection coefficient right there, and our transmission coefficient is going to start at 1 and drop down to 0. And it's got to actually kind of go up and then down, right? Right, so it's supposed to be my transmission coefficient right here. So over here, though, yeah, I'm narrating as I draw. My apologies. Right, so we had, again, so here, right, as we took it was just the reflection coefficient, draw my life. No. So when this was negative, you square it, you get a positive. When this crosses 0, this dips down to 0, and then it rises up to 100%. Here, right, it starts off, it actually dips down a little bit and then rises up, right, because these have to add up to 1. So I didn't show the dip very well. I tried to redraw it. Rises up to 1 right here at Brewster's angle. Over for our S polarization, it's going to be a lot simpler though, right? This just starts off here and rises up to 100%. And this starts off here and, starts off at 100% and drops down to 0 at 90 degrees. This is our transmission, and that's our reflection coefficient. Right. All right, so one of the things that means, though, is at Brewster's angle, suppose you've got light that is not polarized. What is light that's not polarized? That is light that has both polarizations, or another way to say it is has all polarizations, but that means if it's got all polarizations, then there's equal components of both polarizations present. So at Brewster's angle, though, if you get a reflection, only the S-polarized light is reflected at Brewster's angle, right? Because the reflection coefficient isn't 0 right here. Whereas at Brewster's angle, for the reflection coefficient for P polarization is 0. So you can take an object like a window or even your desk or something like that where there's reflection, and if you've got polarizing sunglasses or a polarizer, you can look at it, and as you turn the polarizer at one angle, you'll see plenty of reflection. The other, nothing will get particularly dimmer except for the reflections. And I had tried this before, but I misplaced my stuff. I don't know how well it's going to work. Let's see. No, wait. Oh, you're seeing the reflection of the other light. Ocean and sunglasses. Yes. All right. So the perfect example of this, right, is if you do boating, right, and you've got polarizing sunglasses, right? The point with the polarizing sunglasses is it cuts down on the glare off of the water or off of the road if you're driving, or off of or off of snow if you're skiing. So those are good anytime where you're trying to reduce glare off of a horizontal surface. Polarizing sunglasses will be great. They will do weird things with your laptop, because your laptop, so we'll talk about in a moment, what your laptop, most of these LCD displays have polarizers on the front end. And we'll talk about where, yeah, so does the glare have the same polarization direction? So here, let me take a step of this and we'll draw a quick picture to understand what's going on with that. I forgot to pre-set this up. Ew. Pilots don't wear polarizing sunglasses? Oh, because it messes up reading the instrumentation?
Yeah, actually, I flew in a modernized Cessna, and everything's digital now.
Right.
So so even the basic sensors and displays are all digital. There's nothing analog left.
Right. So it's going to mess up. So you wouldn't be able to see all those screens potentially.
And
Yeah.
also, a glare. If you get rid of a glare, that's a bad thing because a lot of times when you're flying, if you see a glare, that means there's an object maybe you should be looking at. And if you're polarized
Uh,
sunglasses, you might miss it
all
because it will
right.
drag your attention.
Yeah, 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 yeah. Cool. All right. So let's understand actually what's going on with it with our light. So here's going to be our surface of the water right here, or of the snow or the road or whatever. Um, and here's the sun, right? And let's draw a ray of light coming, and let's do it near Brewster's angle. So ray comes down like this, and it comes up like this. That's fine, but let me draw which way the polarization is for this light. So one way is we could have polarization this way, perpendicular. So the electric field points that way, and it's oscillating between pointing that way and that way. Or we could have it coming out of the page, right? And so that's going to be like this and that, right? So the polarization is both. Um, so that's what we would call S and P polarization. The one that the arrow that goes like this, yeah. This arrow right here would be P polarization. It's parallel to the plane of incidence, which is your screen, and then the circle with the dot and the X for the vectors going in and out of the screen, that's your S polarization. And then at Brewster's angle, though, we get zero reflection of the P polarization, and you get complete polar. You get some reflection, not necessarily 100%, but some reflection of the S polarization. So here, let's just say right here, both polarization, right? And so here, this is only S polarization. And because the ground is always this horizontal plane, this is going to be horizontal. So the sunglasses that you wear, so here, this is going to be really disturbing. Here's your eyeball, right? And here's your sunglasses right there. Right? The sunglasses are only going to let through polarization. Here, I got to pick a different color. They allow that polarization, but they don't let through. They cut out the polarization, um, the horizontal polarization, the polarization that is going in and out of the screen. Right? And so that means you can see, you don't get the glare up off of the water. You can see into the water, which is good if you're like fishing or something like that, but not good if you're trying to like avoid something on the ground. So if you wear your polarizing sunglasses and you look at a storefront window, you're going to get lots of reflection, potentially lots of glare off of it, because that's an interface, a surface that's oriented vertically instead of horizontally, right? The normal to it is horizontal. The surface itself is vertical. So it's basically at a right angle to the kind of surface that the glasses are designed to cut down the glare off of. So it will allow through all the glare off of a window, something that's oriented vertically. So you're gonna say, well, not all the light hits at Brewster's angle. Some of it's at an angle that's not Brewster's angle. And so what happens though is, if you remember the previous slide, right? You get some reflection, but not as much reflection of the P polarized light near Brewster's angle, right? It's only when you're quite a ways away from it that the reflection coefficient comes back up and is comparable to the reflection coefficient for S polarization, right? So here, this was our reflection coefficient, R 90 degrees. as a function of the angle of incidence. And so long as we're, kind of in this region right here, I don't know why I scribbled, but right there, right, you'll get some reflection, but you won't get that much. And that covers a pretty broad area. Actually, I drew the curve maybe a little bit sharper than it ought to be. If you look at the curve on your in the textbook, it's much, much flatter than that. So that's why the sunglasses work, even though the light is exactly at Brewster's angle, because it reduces the intensity significantly. Cool. Let's talk for a moment actually about how polarizers work. What are these polarizer things? And we can do more stuff with those too. If you've got two polarizing sunglasses. Here, let's just do this. Actually, let's do this over here. Here. Could have done better without all that. Okay, so here, this is my polarizer. And let's say we've got light coming in like this, right? And it's polarized, it's got its polarization some angle right here. And so what does that mean? That mean that we've got E, our vector right here, equals E naught. And I'm going to write this just as a complex amplitude because I'm going to write a vector for its polarization direction. Let's have it going in the Z direction right now. And so I'm going to write a polarization vector n hat, right? Where if it's going the Z direction n hat, we could give it some angle. Let's call it cosine of theta in the x hat direction plus sine of theta in the y hat direction. The reason why I'm choosing cosine and sine as the coefficients is that guarantees that this is a unit vector, right? Because we take the magnitude of this vector, and so that's going to be the square root of the sum of the squares. So you get cosine squared plus sine squared. Oh, take the square root of that. That's 1, right? So now, what does the polarizer do? So in this case, I've drawn the polarizer. You see, it's a whole bunch of lines that are oriented horizontally in this particular case. And so the polarizers have an axis. The polarizers are anisotropic. So it could be, if you're dealing with microwaves, polarizers, one way they make polarizers is just have an opening with a whole bunch of wires strung across it, all parallel to each other. So our polarizer has an axis. And so in this case, I've drawn it horizontally. So in these plastic ones right here, what you have are metallized polymers. So it's so the polymers are long molecules and they've got metal in them. And so you can get conduction in one direction, but not in the other direction. And so it basically allows one component of the wave to go through, but not the other component. Yes, so I'm not quite sure how the metallization of the polymer works, but it's made under some sort of stretching tension so that they're all aligned in the same direction, right? Because otherwise you just have a jumble of these metal stringy things. Play intro music. I don't know what that means. That a show? How is it made? vague memories, vague awareness of its existence. Okay, right? So in this case, right, after we let this through, we're going to have, whoops. So in this case, if it was horizontal, right, we're going to have E transmitted, this vector, oh, and this is a complex vector, right, we'll have E naught tilde, right, or still, or E to the I, kz minus omega t, right? And in this case, though, we're just going to have cosine of theta x hat, right? And so now we've basically, it's the exact same thing, but only allowing through this component right here. And we also remember our intensity is 1/2 epsilon v, right? The amplitude squared right here, but we're going to point, I'm going to underline a couple of the parts right here, right? Basically what we've done is our amplitude now is this times this, right? And so we're going to call, here's our incident, right? And now our transmitted intensity is going to be 1/2 CV E naught cosine of theta, whole thing squared. This is an epsilon, not C, epsilon, right? And so so what we can do is we can take a look at the transmitted intensity as a ratio of the incident intensity, right? This would be our transmission coefficient, right? I can say transmission coefficient is equal to this thing right here, right? And so that's just the, oh, well, basically just cosine squared of the angle, right? And so in this case, I said, okay, we've oriented the axis of the polarizer horizontally, but really what we could do is this theta in this case is the angle between the polarization and the polarizer axis. So, and so two things, right? So let's put a box around this. Give me a second. This transmission coefficient right here. And I'm also going to give this a name. This is called Malice's law. So before we get into this, though, right? So after the polar, not only have we rejected some of the light, only allowed through part of the light, but we've also created a new direction for the polarization, right? The only surviving electric field is polarized in the direction of the polarizer, right? So I can take a regular polarizer or your regular polarizing sunglasses, and for one thing, they look a little bit gray, and that's partly because if the light you're looking at is unpolarized, half the light is going to be a component along the wrong direction. So it's already cutting down the light. And then if I have two of them, I can take them, and here, let's see, can you see my face through here? I'm going to actually close the window so you don't see as much reflection behind here. There we go, right? So you can see my face through here, right? But I'm going to take one of them and I'm going to start to rotate it and watch what happens. So I rotate one, right? We're at 90 degrees now. There's zero transmission, right? Cosine 90 degrees is 0. And I'm going to keep rotating past that, and we start to get transmission. By the time I get to 180, it's all there. Yeah, where'd he go? And what's really crazy, right? If I had a third one, which I do, I don't have enough hands to do this, right? So I'm going to take this and make it so, right, where'd he go? You can't see me. I'm right here. I'm going to take a third one right here. I'll take it out of the wrapper. Camille and Nate know exactly where these are from. These are the ones I shipped out a bunch of these for advanced lab. So here, this one's at 45 degrees. No light coming through, right? You're just seeing the reflection of stuff of the camera. And I stick this one through, right? And this cuts down half of the light too. I stick this one at 45 degrees between, and now you can kind of see me through there. Not very great, but you can still see me a little bit. What's the deal with that? So nothing coming through. This one here cuts out half the light, but when I put it in between these, you can see me some. When I put it in front, nope. We're
Ah, I got it.
What?
You're changing the alignment of the light through the first polarizer, and then
Uh-huh.
you're changing the direction again through the second,
Yep.
and then you're lining up again for the third.
Yeah. So when it was, the first one, let's say it let through light like this. And then when I just had the two, the next one would only let through light with the light component like this, and that's 0 of them. But so here's what Derek was saying, right? First one, only this polarization is letting through. Put the 45-degree light, the 45-degree axis like this. I misfound it. Yeah. So now we're letting through, well, half the light has a, right? So it's cosine of 45 degrees, which is 1/2. But when you square that, you get 1/2. So half the surviving intensity makes it through, and now it's polarized like this. And then you project onto this right here, and half. And so again, cosine of 45 degrees between these two gives you 1/2. Square that, and half the light comes out like this. So you're getting of the light that made it through the first polarizer, you're getting half, and then another half, two successive steps, two successive projections, but going through like this to this, like this, gives you 0 if you try to do it all in one step. What's happening at the atomic level to do this? Again, so our light, right? So this thing right here, right? You can decompose it into being a sum of two vectors like this. And so only this vector right here survives. So only this like this survives. And then the same thing like this. So successive projections are different than just jumping straight to the end. And those of you who have taken quantum mechanics, this is kind of like taking a spin up through a Stern-Gerlach analyzer, taking the spin up and then running it straight into spin down, you get nothing out of it, right? But if you take a spin up z direction, then take only the spin up in the x direction, and then take from the output of that, take the spin down in the z direction, you'll get a quarter of the original intensity out, because half of the spin up in the z direction survived spin down in x, and then half of that survived the spin down into z. Successive. So how is it that we are effectively, so I'm talking about mathematically predicting vectors. So at the atomic level, what's going on? So one way to think of a lot of these things is to think of the electric field starts the molecules, or the electrons in a metal starts them oscillating back and forth like this, right? And so what we're going to see later on, right? So we're polarizing the material, right? But it's an oscillating electric field, so the polarization is oscillating too. And then as we get these oscillating charges because of the oscillating polarization, what we're going to just briefly touch on kind of qualitatively, an accelerating charge radiates. And so basically, if you've got a dipole that's flipping up and down, or polarization is going up and down, up and down, up and down, dipole that's flipping up and down will radiate in directions around its belt, but it won't radiate. The only direction it won't radiate at all is along its axis, right? And so by doing these we're exciting these dipoles oscillating, and they radiate field in a bunch of different directions with a bunch of different polarizations, except for along their axis, right? And so they will re-radiate. So normally, a normal material, right, you can actually understand the index of refraction this way. You come in with a wave going like this, oscillating like this, and that starts a dipole oscillating like this, and it doesn't re-radiate up and down. Basically, it just, you get a bunch of interference from a whole bunch of the dipoles in the material, and they're re-radiating out in this direction, but the interference causes only, you get constructive interference in the forward direction and destructive in the sideways and backwards direction. And so that can actually create a little lag, right? You start the thing oscillating, and then it re-radiates again, and that's delayed the wave a little bit. So it looks like the wave is actually slowed down, slower speed of light in the material, right? And that's where we get an index of refraction from. So we can understand this stuff that we've got through kind of this macroscopic treatment of polarization in the whole material. We can go back down to the microscopic level and think about absorbing, the wave will start mechanically oscillating the charges, and then so the wave gets absorbed in order to do that, right? You have to have conservation of energy, but then those charges re-radiate, they slow down, and electric and magnetic waves come back out of them. But the direction and the phase may be changed by doing that. And that's partly how we can understand these things. We can even explain actually Brewster's angle this way. We can have light coming in and it's polarized a certain way, and you get the dipoles in the second material oscillating, and they're oscillating in a certain direction like this, if the interface is like this, as they're transmitted along. And so you cannot have any radiated electric field going out in this direction. It can go in this direction, this direction, this direction, right? And so basically when you get the angle of reflection is at 90 degrees to the angle of transmission, then for polarization in the plane like this, you can't get light coming that direction, right? But if it was polarized, if it was S-polarized in and out of the plane, sure, you can have light come off this way because that's around the belt, the waist of the dipole. That's not on the axis of the oscillating dipole. Do you have to understand all that? No. I want you to just have a flavor of it, that we can actually reconcile this macroscopic description and the microscopic description in the same way that like working with conservation of energy or conservation of momentum were both true in Fund 1 for mechanics in the right circumstances, but working with different ones was easier in different situations. Yeah, this macroscopic view, the microscopic view, two different pictures should produce the same results, but will be different. One will be more convenient in some circumstances, the other will be more convenient in others. Cool? Wow. Yeah, I know. I was doing lots of like, we'll have to do that in all my free time. Here, while I'm, like we said, what was this? Yeah, it's good stuff. It's fascinating stuff. I'm going to talk about something even more like crazy mind-blowing once I take this. Uh, um, yeah, so we got Staying Alive, we got the Hokey Pokey, all kinds of vector dances. All right, Brewster and Malice's Law. All right, so let's.
I thought it was fun to watch people do the right-hand rule during an exam. Just imagine the hokey pokey.
But it's the finger hokey pokey only. Cool. So, all right, that's Brewster's angle. Let's put a pause right here and actually take a look at the properties of materials. So far we've been saying, okay, yeah, you can have permittivity and permeability that are different from what they are in space, so that you get slower speed of light in the materials. Yeah, sure. All right. So far, when we've been talking about epsilon and mu, so and then also the index for refraction, right, which is epsilon mu over epsilon naught mu naught. I don't know why I'm writing so big. Right. So other thing though, right? So it's just been like, oh, you got a piece of glass, you got some water, you got like, right? It's just like we've got a bunch of this stuff, right? But the other thing is, here, let's do it this way. The other thing is we can also make structures. And here, where the size of stuff, that's an N right there that you're pointing at. Sorry. N. Oh, God. Right, where the size of the structures is smaller than the wavelength. And these structures, this is why I can't go back and forth like this. Lambda, crappy lambda. So much smaller than, here, let's do it one more time. Whoop, whoop. A little bit better. That. When I say structures, a lot of the times they're basically capacitors and inductors. So you make a material that's just got tons and tons of these little structures, like smaller than a wavelength, which if you're dealing with like radio waves or microwaves, that's not too bad, right? That could be, meter or centimeter scale, right? But if you're dealing with light, you're talking about like, hundreds of nanometers, and that starts to get complicated, particularly if you're talking about three-dimensional materials, right? But it's not impossible. We make transistors, we make integrated circuits, microchips, where the features, the transistors, are on the order of like 13 nanometers or so. So yeah. So these materials are called metamaterials. Ma. Right. Supposed to be even. We can even get permittivities that are less than 0. In other words, right, if you apply an electric field, you induce an electric field pointing the other direction in it. And same thing with a magnetic field. And if they're both negative, right, that was an and or. If they happen to both be negative, and by convention, and actually, like if you look at what's going on, is that your index of refraction is less than 0. Wait, was that a comment? Yeah, sounds like something out of science fiction or comic book science. Yeah, yeah. Well, where does he get these powers? Metamaterials. And this is something that started to be introduced like in the very, I don't know, late 90s or no, early 2000s, early 2000s. And they are big. There's all kinds of technological applications that come from them, right? So if you can, it used to be you would have to blend up the right blend of like glass or something, right? But to structure, to change the index of refraction, and even then it would be like you could make small changes. But here with metamaterials, make big and like really like bizarre changes to yeah to the properties of the material. So I mean, just remember here, right? We had, all right, Laplacian of our electric field is 1 over v squared. Oh, so this is a different kind of thing, right? We can have materials that have all kinds of strange properties, like thermomechanical properties. And there are things that do that, or ones that like you push on them one way, and usually like if like I don't know, like I'm not quite done. That's a second derivative, d squared dt squared. Sorry. Usually, like if you got, I don't know, like a bag or a marshmallow, you squeeze it this way, it expands out this way. You can make somewhere if you squeeze it this way, it contracts this way, right? But those are mechanical properties of these metamaterials. We're specifically talking about optical metamaterials, right? There are other kinds of. I don't know why I keep misspelling that. Yeah. So we've got that, and so right this right there that allows positive and negative.
What does the negative uh, index of refraction do?
Yeah, so remember, what's our index of refraction? V is equal to C over N. So if our index of refraction is negative, that means that your velocity is negative too, right? V equals C over N. So what? Right? So let's take a look at the consequences of this. And I'm going to have to like run over into to the side too. So the first thing is waves propagate backwards. Lions and lambs lying down together. No, all kinds of stuff. Let's take a look at Snell's law, the law of refraction.
What would propagating backward actually achieve?
Yeah. So this only makes sense within the material, though, right? So here, let me draw my material. Here's a thin slice of the material, right? And I'm going to send in a wave like this. And so I'm going to draw in time going vertically. So my wave goes in, that's the pulse of the wave, right? Like that. And so a little while later, right, it's advanced. So it's really hard to draw here. It's going up like that. And then over here, right, it's actually coming from the far side of it, like that. And then a little while later, it's mostly it's starting to merge right here, and it's mostly over here. That's down here, sorry. So it's coming out right here, and then a little while later, it's come out like that. So within the material, it's run backwards. What? Let's take a look at the law of refraction, right? We've got n1 sine theta 1 equals n2 sine of theta 2. But now, this one right here is negative. Yeah. All right. Harry asks, how did the opposite side of the material get the information to start the wave heading backwards, right? Because it seems like if this was thick enough, right, that would be like information traveling faster than the speed of light. Like the far side knew before the near side knew, right? And there's an answer to this. These materials work over a finite bandwidth, right? Their epsilon and their mu is a function of frequency. So you can't, what that means is, right, it only works for a narrow range of frequencies. And so what that in turn means is you can only have fairly gradually changing waveforms, right? I drew my wave not as an infinite like sine and cosine wave, but actually as that pulse. But because this works for a fairly narrow range of frequencies, this pulse has to be pretty broad right here. Right? So this is the envelope. So the pulse itself is a whole bunch of oscillations within here, but this has to be fairly broad. And so that means that it's got this long tail at the end and at the front. So the front of the tail, right, has information about the whole wave through the Fourier transform, like on your homework. And so that front of the tail, when this is right here, the front of the tail is actually already reached here. So it's not like information has gone faster than the speed of light. And energy is still actually flowing forwards, just this waveform, right? So there's weird stuff going on, but we actually haven't violated relativity. But you really have to look really carefully at it to see like how to actually work this way. But here, let's take a look at the law of reflection, law of refraction. So it turns out you can actually build materials where the speed of light's propagation through them is faster than the speed of light. But again, this bandwidth issue only works, makes it so you can't send information. Well, yeah, what does that achieve usefully? I don't know. Nothing, right? Because you can't send. So for this material right here, so the light, so material light going faster than the speed of light, you might be able to do something. Yeah, you can publish all kinds of stuff. I'm going to show you, right? This light going backwards, that was just because I said, oh, the index of refraction is negative, but we haven't gotten to all the consequences. I got a list of like 5 of them, and you'll see they start to get pretty useful, interesting after a while. So let's take a look at this right here. So right, the light, that's a horrible ray. But that's my incoming ray of light, right? And so normally, right, we would get something that comes out at a slightly different angle on the opposite side of the normal, though, for the transmitted light. Instead, what we get, because n is negative, the only way for this equation to work is if the angle 2 is also negative. So you get refraction on the side of the normal, right? So negative. So this means, what was the comment? Could you send optical signals to a receiver faster than receiver faster? Yeah, you could. You can't violate the speed of light, though, right? Again, because there's actually the part of your signal is going, is in the very early part. So the materials where the index of refraction is less than 1, so the speed of light is greater than 1. One way to build it is actually just have an amplifier. And the material's going faster than the speed of light, but information isn't. The envelope of the pulse isn't. So one way you could do that is have your pulse go in, and the very beginning of the pulse, right, you've got the amplification up high, so you make that pulse, the initial, that leading edge, that very beginning slanting part, much taller. And then as it propagates a little ways in, you turn down the amplifier so that you cut off the rest of it and make a new peak of the pulse. And that's farther ahead. Than where it would have been without it. And so that's really leading, and it only worked because there was still information about the rest of the pulse in that leading edge, right? So you haven't violated the speed of light, you haven't violated causality, but you could, within a big material and you're really, really fast, you could make it so that the pulse goes through faster than the speed of light. What? No. So there are lots of different things. For a regular old pulse, the light isn't the info, right? But the light is the info. But we're going to see, actually, in our next class, or the one after that, that there are actually a bunch of different speeds that are relevant. And I'm going to share with you, you can actually talk about, like, when you're talking about speed of light, there are actually like 7 different, or 8, depending how, I don't know. It depends how you want to characterize it, right? There's C, the one that this constant that keeps popping up in our Maxwell's equations. There's the speed that light travels. There's causality, the limit, that speed limit. There's the top of the pulse. There is what we're going to see, group velocity versus phase velocity. There's information velocity. Most of the time, those are all the same thing. But under the right circumstances, we can actually set up situations where there are differences between, well, when's the top of the pulse go by, or what is the phase velocity, or what's the group velocity. We can actually look at situations where we can set up situations where those are different, and there are only some of those that are restricted to be below the speed, below, C, 3 times 10 to the 8th meters per second. So kind of crazy, but we'll come up to that in another couple classes too. So this has to be negative 2. All right, so all of a sudden refraction's working kind of differently. No, it's not necessarily electrons. Information, something that could cause something else. Oh, that's pretty vague. We have to get it starts to be a lot of work to define these things. Here, I'm going to take this up and over here. Here's another consequence, right? So we've just seen that refraction works differently too. So that means that it turns out that you can build what's known as a super lens, right? Who was saying that this sounds like superhero, like, you know, you got superpowers from using metamaterials, right? You can build a super lens. What's a super lens? That's it's a flat slab that focuses light. That'd be pretty cool. You don't have to make this curving surface. I mean, you can get those flat plastic Fresnel lenses, but really what they're not completely flat. You can run your finger on them and you can feel they're rough. They've actually got a bunch of concentric rings, but once the rings, the thickness is such that you get a delay of 1 wavelength, they reset the thickness because all you care about is phase modulo 2 pi. So this is just straight up flat lens. That'd be pretty useful. You can make much smaller optical components. We could, so with regular bulk materials, where you're using an index of refraction greater than 1, you're limited into about how well you can focus a beam of light is limited to about the wavelength. You might be able to get down to half a wavelength or so. But here you can get super resolution. Focus to a spot. Smaller, a lot smaller than the wavelength. And that would certainly be useful, right? You could build super microscopes. You could, right, when people make the microchips in your, the integrated circuits in your computer, what they're doing is they're actually exposing the material with light to basically print the circuits. And right now, right, they have to move to like extreme ultraviolet, so they get really short wavelengths, so they can make these small features and use all kinds of extra things. So if you could focus smaller than the speed of than the wavelength of the light, then you could print even smaller circuitry. Wow. Oh yeah, so that's called super resolution. So that's, again, so would that be useful? Well, I mean, ask the semiconductor industry and they would say, heck yeah. Yep, I just wrote that. Do you see that? Yes. People have made them. It is true. It is true. You can look this up. People have made cloaks in the radio waves. They've only been in 1 or 2 dimension. They're getting them down into the infrared. Again, limited dimension, limited bandwidth, right? So far, so yeah, there is definitely interest by military and such. So what would happen is the light would curve around, right? This your object, right? And so light that was coming from behind would just would curve around and continue on to a viewer. So, and if you were to shine a light on it, the light would just keep going. It wouldn't reflect back to you, right? Yeah. So consequence one, not exactly. No. And so part of this involves like having variations too, so that you kind of guide the light around. Um, uh, yeah, sure. Like all kinds of, right. So in night vision, well, okay, the night vision's still usually pretty broad band. It all looks green because it's projected onto, they take the light and there's a phosphorescent screen from the yeah, devices oftentimes. But yeah, totally. Or radar, right? Radar cloaking, very, very, very useful. And it would actually be easier to build something for radar than for, right? We've got stealth technology that doesn't cast much reflection, but you could also make it so you don't cast a shadow as well. Yeah, pretty cool stuff. So these materials, anyways, they're called a couple different names. So in the past, I've had people actually like research this, but you've got enough to do. Um, yeah. So these are sometimes called either negative index materials, right? Because it's got a negative index of refraction. They're also sometimes called left-handed materials. So why are they called left-handed? Right, so remember B in our wave is 1 over V K cross E, right? And so having V negative flips the handedness. Handedness, I don't have enough space for that. But yeah. So you can do all kinds of cool stuff with, you know, their optics itself, right, relies on, you know, having an index of refraction and these interfaces. But now imagine that you're not just limited into having n equal to 1 and maybe up to like, you know, 1.5, 2, right? Now what happens if you can start allowing n less than 1 or n negative, right? All kinds of new optics. Yeah, let's talk about that later on the night vision thing. So, um, uh, yeah, so they have made these materials for radio waves. They have made these materials for the infrared. Um, they've made them in like one dimension for narrow bandwidth of visible light. Yeah. So the initial ones were basically, you know, often like sets of rods and rings and stuff like that were acting like uh, capacitors, rings with gaps. Oh, and the rings were acting like inductors, but the gap formed a capacitor. So you had these resonators, and so they would resonate out of phase with the wave, and so re-radiate out of phase, and so hence the negative index. So yeah, it's people only really started thinking about these seriously. So someone speculated about these in like the 60s, and people talked about these different speeds of lights and stuff like that around the turn of the 20th century. But it was only the beginning of this time, beginning of the 21st century, that people started really recognizing the um, implications of this and actually building them first in the radio waves and microwaves and then infrared. Yeah, dimensional. It just means that you have to be looking within a certain plane, right? And so it's possible to build cloaking devices and stuff like that with regular optics, so long as you're not like right in the center. But they only work for a really really narrow set of angles of view, which isn't particularly useful. With these metamaterials, you can make one that would work in all directions. The problem is making it so that you control the index of refraction for light propagating in you know, in 3 dimensions. It's pretty easy to set it up so that it looks the same within a plane, but then once you go out of the plane, then it gets a little bit more difficult. So for example, the ring and resonator things, they had kind of in a plane, a set of rings and rods going like this, but what happens if you're going like this and the rods aren't oriented the right way? Yeah, so, and to do this, like, so there's now the fact that we can tailor the index of refraction of materials basically at will. Maybe not for visible light, but for other types of stuff, other wavelengths for radio and microwave, and eventually, right, the technology will come where we can do it with optical. The fact that we can locally tailor the index of refraction is kind of like locally varying the speed of light, right? And so people have started to take the mathematics of general relativity, where the curvature of space, right, where space gets curved, and so going on just plain old flat space, it seems like its space is getting stretched and so on, and that's because you're locally varying the metric. So that is like locally varying the speed of light in effect. So people have taken the tools of general relativity, that's very kind of like theoretical, like, oh, that's really cool, but what are the applications except for me, keeping track of GPS and stuff like that. They've taken that mathematics and used it here to kind of reverse engineer, I want to accomplish this, how do I design the right layout of index of refraction to accomplish this optics task? So pretty cool stuff. And again, another example of why even kind of this fairly esoteric, abstract physics like general relativity can actually have technological applications too, if not the general relativity, but the mathematics developed for it is now used. It's called transformation optics. Can be used for designing optical devices. Cool. Okay, so you thought that was weird, where we had index of refraction that was negative. Next class, we're going to make an index of refraction that's complex numbers. All right? Whoa! Yeah, it'll be cool, right? More and more abstractions, more and more power. I will. That's a teaser. Make sure you come. Tune in next time we go complex. I know, our world is just upside down. You can go faster than light, the speed of light. You can have light that's faster than the speed of what? Complex index of refraction. Yep, indeed. You just can't violate causality. Oh, I can't clip this yet. I gotta wait for all the notifications to disappear. See y'all.